Hello, Professor. We are Team 16. I am Shodita, and my team members are Anup, Vamshi, Rohit, and Kalyan. Today, we are presenting paper 16, and the topic is self hiding behavior in Android apps, detection, and characterization. I would like to start with the introduction. So, here, mobile security research has primarily concentrated on malware activation, malicious payloads, permission abuse, and sensitive data leakage. Little attention has been paid to deceptive mechanisms that are critical for malware success. Malware accomplishes this by employing a variety of SHB, which is self hiding behavior, such as hiding the app, hiding app resources, blocking calls, deleting call records, or blocking and deleting text messages. Applications or apps that conceal their activities are fundamentally deceptive. App marketplaces and end users should treat such apps as suspicious. However, due to its nature and intent, activity concealing is not disclosed upfront, which puts users at risk. In this paper, we focus on the characterization and detection of such techniques. For example, hiding the app or removing traces, which we call self-hiding behavior. Surprisingly, extremely popular harmless apps like Airbnb, Truecaller use certain SH techniques for user convenience. We believe that self-hiding behavior is fundamentally deceptive and that having tools that detects SHB accurately and early is critical. So we address these issues and the Android platform in three ways. We shed light on SHB through detailed characterization. We build a self-hiding behavior detecting tool based on static analysis, and we demonstrate how our approach to identifying self-hiding behavior can be highly effective at exposing malicious apps as well as deceptive practices in benign apps. We will discuss detailed characterization of self-hiding behavior. SHB is divided into three major categories. So SHB that involve app objects such as hiding the app's presence, SHB that block or remove traces of remote communication such as blocking calls or deleting text messages, and SHB that subvert the system's reminders such as hiding notifications or muting the phone. We use a tool comprised of a suite of static analysis that identifies potential SHB in an Android app. Our tool operates directly on APKs, the format in which Android apps are distributed, and does not require access to the app's source code. We show that SHB can conceal an app's presence or activity as well as cover up its traces, such as by blocking phone calls, text messages, or removing calls and the messages from logs. We expose the frequency of 12 such SH behaviors using a static analysis tools on a large dataset of 9,452 Android apps. Our method is effective. It has been discovered that malicious apps use 1.5 SHBs per app on average. When used to distinguish malicious or benign apps, our method has a high precision and recall. Combined F measure that is 87.19%. Our method is also efficient with an average analysis time of 37 seconds per app. Our findings and analysis tools. So we are while popular Android security could be improvised, researchers from antivirus firm G-Data discovered that more than 750,000 new malicious Android apps emerged during the first quarter of 2017, with the total number expected to reach 3.5 million by the end of 2017. As a result, there is ample evidence that the threat level for Android users remains high, and there is a strong incentive to detect and eliminate malware before it is published on Google Play or reaches users' devices. So now my friend Rohit is going to continue from here.
Hello, Professor. This is Rohit. Now I'm gonna explain self-hiding behaviors. In this, we provide a comprehensive description of self-hiding behaviors. Self-hiding behaviors is nothing but which hide the app or its action from being viewed by the user. A user could employ three main approaches for the presence of malicious app. The first one is inspecting app objects, and which includes icon, app, and activity. And second one is analyzing remote communication, which includes MMS, SMS, and phone calls. And third one is checking system reminders, which includes system dialogues, sound, system logs, notification, and recent app list, etc. And in this, we have two major issues with this approach. I'll be going through it. And the first one is it requires a high knowledgeable user who performs such inspection regularly on daily basis of checking the apps. And the second one is malware activity attempts to escape from such identification. In these approaches, the first one is app objects. In that, we have three main things like icon, app, and activity. In this, I'm gonna explain you the first one, that is hide icon. After installation, begin app add their icon to their home screen. To hide itself, a malicious app removes the icon so the user cannot notice the app's presence. Modifying the app's manifest file to remove the app from the default launcher, that is the home screen. This can be done by deleting the category Android intent launcher from the app's main activity session in the manifest file. Calling an Android API method to disable the icon at runtime. This can be done by invoking a method called setComponentEnabledSetting. In this, we have the next one is the hide app. In this, when the harmless applications are running, they commonly appear in the running application list. To contrast, malicious app can run as a service in the background, so it does not show up in the list. In order to automatically start the malware as a service without the user clicking the icon, a malicious app creates a broadcast receiver class and registers it to receive a certain events like SMS received and boot completed. After receiving one of the registered event, the malware broadcast receiver launches the malware as a service in the background, which results that the user cannot see the malicious app in the running app list. And coming to the final one in the app objects, we have hide activity. Most malware runs as a background service. However, starting in the Android version 3.1, apps cannot create a service without having an activity associated with that service. Therefore, a malicious app must first create an activity. Next, to hide the activity, the app can employ the two main approaches: making the activity transparent or destroying the activity. before it visible. And in these two activities, the first one would like to render an activity transparent, malicious, which need to be actively main layout transparent. And the second one would be the destroy one, which call the call function in one of the three life cycle callback method. The next remote communication will be explained by my friend Anup.
Now I'm going to discuss remote communication and system reminders. In remote communications, we have four types. They are delete message. Malware is known for sending SMS or MMS message stealthily and in the background. As a result, several antivirus programs concentrate on this to detect malware. Android saves a copy of this SMS in the background in inbox or outbox respectively. The malware must erase this copy to hide its tracks. On a content URL, the virus commonly calls delete in inbox or outbox to delete the message. The example of such a malware is xtavoad.a. This one delete a message when it is received. The next one is delete call log. Android creates a record in the call log after making or receiving a phone call in the background. Malware must remove this entry from the call log to hide its tracks. The Save Me spyware is an example. Save Me provides a service that can make a background call based on the malware server instructions. Block message. After a malicious app sends an SMS to sign up for a premium rate service in the background, the service provider will send a confirmation message. To keep consumers from noticing, the malware must call abort broadcast to filter the received message. Trojan Fakeback B is such an example. Block call. For malware, this is a part of the botnet. The command and control server could call the infected phone to ask the malware to perform certain services. The CNC server is encoded in the phone number. The malware must block phone calls for consumers to be aware of this. The ringer mode is set to mute to prevent the notice of this income call, and the phone call is disconnected if the virus receives an intent.action.phone state, and the caller's number is in the CNC server. Its call log entry is likewise deleted, effectively erasing all evidence of the phone call. The malware fake AV, for example, utilizes end call intent to cancel an incoming call. System reminders. When something happens in the Android device, the system will send some reminders or notifications to let us know what is happening. What malware does is it will stop these notifications and messages from appearing. Such examples are hide alert. System dialogs could reveal the presence of malware by displaying alarms, user account balances, or other abnormal behaviors to the user. To avoid this, malware has to dismiss the system dialog by broadcasting the intent action close system dialogs. So we cannot see any system dialogs by making use of this command. Hide notification. Apps can send alerts to the user by generating a notification on the notification bar. But the malware can delete notifications by calling notification manager's methods cancel or cancel all when receiving these notifications. An example is malware BIOS native malicious code.apk. It's an app by using which we can delete the notifications or we can hide them. Mute phone. To cover their presence, malicious apps often resort to muting the phone or disabling the vibrate function. So the device will not vibrate or ring, so we cannot hear that. To prevent the user from hearing alarms, notifications, phone calls, or incoming messages. This can be accomplished in a variety of ways. Switching to silent mode or putting it on vibrate mode, setting phone to mute, or adjusting the volume to the lowest possible level. An example is Frozen iBanking. System reminders. Exclude from recent app list. Whenever we use a app, it will comes under recent apps in the background. To prevent this, malware can set the flag exclude from recents in the manifest file, or by calling activity manager set exclude from recents. An example is Trojan Malap. Delete system log. Android saves system activity into the system log, which can be viewed via the logcat. Malware can call adblock logcat to delete the logs if the phone is rooted or if the Android API is lower than 16. An example of this is Trojan SMS blocker. Next, my friend will continue how to detect the sleeping behaviors.
Hello, Professor. I am Kalyan Kumar, and today I will be discussing detecting SH behaviors. Our first analysis finds whether SH API calls are invoked. Specifically, the analysis starts at an origin. In the first stage, we use control flow and call graph analysis to find whether a certain SAPI call is invoked. Green nodes and edges on the left represent methods and call graph edges. In the second stage, we use backward data flow analysis to find if the call is invoked with certain SH indicating parameters. More precisely, we walk the chains backward until we can find the parameter definition. For example, to detect the hide app SHB, our analysis will check whether the call to context start service is reachable when starting in broadcast receiver on receive. Looking into the detecting research behavior, so did we ever think how to detect the self-hiding apps in your application? So our application relies on a suite of static analysis to detect self-hiding behavior. The figure shows an overview of our tools designed which sends a bytecode to suite flow or flow drive for analysis. This kind of analysis may be called the pair action analysis. It is used to analyze activity to attribute. And from here, there are a set of detection rules which are applied and checked thoroughly, and Hess's behavior reports are generated. So to be more precise, we pass the bytecode to SuiteFlow Droid, which performs basic tasks such as analysis, call graph analysis, as well as fixed point computation to deal with loops and recursions. As soon as we complete the recursion, we perform our code analysis on both the bytecode and as well as XML files. Finally, a report detailing the potential itself hiding behavior is produced. So as we discuss the static analysis here, this control flow analysis and the data flow analysis, the green line indicates the edges and the diffuse change, which is the reverse graph finding research called invocation. We present this analysis specifically. This analysis starts at the origin of the first stage. We use control flow and call graph analysis to find whether a certain SAPI call is invoked. As we said, green nodes and edges on the left represent methods and call graph edges respectively in the second stage. That is data flow analysis. We use backward data flow analysis to find if a call is invoked with certain parameters as such as shown in the origin and SAPI call for each self-hiding behavior. For example, to detect the hide app, self-hiding behavior analysis will check whether the call to context start service is reachable when it is starting in broadcast receiver on the receive function to check for delete message. On the other hand, we start tracking from broadcast receiver on receiver function to see if we can reach content resolver delete function, and the next we will walk to the diffuse chain backward to see if the argument is content SMS. From here, my friend Vamshi will continue.
Uh, Hello, Professor. I'm going to discuss about pair action analysis, or else called as PAPI in the short form. It's a broad self-hiding category, consists of pair actions, where an app first performs a malicious action, then deletes traces of this action. For this, we have an example. It's deleting a text message after sending it. Our analysis detects 6 types of actions. They are send message, delete message, log, receive message or delete message log, receive or block message, make phone call or delete call log, receive phone call or delete call log, receive block phone call. Our pair action detector uses data flow analysis in a manner similar to taint analysis to see if the data flow from pair start to a pair end. The paired methods and the SHP are listed in the table 2 of the research paper in the figure 4. And the figure 4 shows a code snippet from the real malware save me that deletes a call from the call log. And then while coming to table 2, we have delete message. For that, the pair start is SMS messenger dot send text message or send multipart text message with the parent with having content resolver dot delete. So in the same way, delete call log has context start activity or phone state listener dot on call stage change with the parent content resolver dot delete. In the same way, block message has pair start SMS message dot create from PDU with parent broadcast receiver dot abort broadcast. Along with this, we have block call, which has a pair start broadcast receiver dot on receive, followed by phone state listener dot on call state changed with parent I telephony dot end call. And after this table, we go to user decision analysis. To reduce potential false positives in cases where SAPI methods are also used by benign apps, we perform a user decision analysis that checks whether an API changed the app state. Here, user design GUI is an interactive GUI element. For example, button, checkbox, radio button, toggle button, spinner, picker, or menu. And while going to user decision callback, or in the short form called UDC, is a top level callback method directly invoked as a result of the user action. And the examples for UDC are on click, on check, changed. And while coming to the next point, it's in contrast. Some callback methods are due to decision unrelated actions. Examples for this are on back pressed, on scroll, on editor action, etc. Now we determine that a given callback is an UDC if either of these two conditions is satisfied. The corresponding GUI of the callback is an UDG, and the event to be handled by the callback is a decision-related event. And the examples for this are click. Note that there exists decision unrelated events. Examples scroll and focus change. And while coming to the next point, the corresponding GUI of the callback is an UDG, and the listener of the callback is decision related. Example on check listener, and here we have to note that there exists decision unrelated listeners, and the examples for these are on create context menu listener and on focus change listener. Next, we are coming to activity finish analysis. This analysis detects activity hiding, that is, whether an activity is terminated prematurely before being displayed. To achieve this, the activity calls finish within onCreate, onStart, or onResume, or their descendants in the call graph. Therefore, our analysis starts at the beginning of these three callback methods. We perform a control flow analysis to check whether there exists a path from the beginning of the callback to the callback's end that includes finish. If such a path exists, it indicates potential activity hiding. We name this AF analysis for short. Next, while coming to attribute analysis, the purpose of this analysis is to check whether the app attempts to manipulate activity attributes in order to deceive the user. The analysis checks both the XML manifest file and the attribute related API methods. For example, the liner layout of an activity has an attribute background color. If the attribute value is #000000, that's 1, 2, 3, 4, 5, 6, 7, 8, 8 zeros, the activity is transparent. An app can set the value of an attribute in the manifest or layout files, or by calling certain API methods. And the examples for these are set background drawable, set background color, or set background resource. The another example attribute is exclude from recents, which can be specified in the manifest file or set via the API methods set flags and add flags. And till now we have covered till 3.1.5 in this paper, and from 3.2 section the next group will be continuing, and that group is group number 36. Thank you.
Hi, Professor. This is Ian from Group 36. We are going to present the paper Self-Hiding Behavior in Android Apps, the Detection and the Characterization. These are my teammates, Siva, Charit, Sisindri, Ian, and Funny. We start the explanation of the implementation of the system. We carried out our tool on top of the Sooth and FlowDroid static analysis framework. These framework only analyze the bytecode, so we added modules to analyze XML files. For example, categories and attributes in Android manifest.xml, style XML, etc. Our static investigation module utilizes the two information streams and control stream examinations. At last, the analysis results are delivered utilizing the detection rules. The limitations. The limitations in the system are of three categories. First one is limitations or false negative. Our tool has several analysis limitations. To begin with, assuming the SHB is summoned by GUI association, however, the GUI text doesn't mirror the conjuring of the SHB, the tool won't report it. Hwang et al.'s idea of finding the mismatches between user interface and app behavior could be used to address this limitation. Coming to the second limitation, there were a few apps that due of obfuscation could not be analyzed. For example, TripAdvisor and KCLS. Here comes with improving and precision or reducing the false positives. Our analysis constructed on top of FlowDroid depends on overestimation and handles the reflection local code modularity. This can be the source of false positive. Likewise, SAPI capacities with zero boundaries tend to have all more misleading upsides, and more exact false names and stream investigation would rather further develop accuracy. The third type of limitations are border concerns. These could be different classes of SHBs. The one we found in any case, our rundown of SHBs is is effective at malware segregation, expose a problematic practice in beginning applications. At last, our methodologies cannot precise explicit malware families, such as certain SHBs could range the different malware families. This is expected as our plan objective was at the lower level, programmed SHB identification rather than the clustering malware by the families. Evaluation. We present an evaluation of our approach along several dimensions. First one is the method viable at distinguishing the SHBs? Is the methodology effective? What are the primary drivers of misleading upsides or bogus negative values? We start by dissipating the two datasets utilized in our assignment. Thank you, Professor. The remaining slides will be continued by my friend, Funny.
Hi, this is Lankesh. I'm continuing the explanation about the datasets. And our first datasets, which we name as MA198, contains 198 malware samples that were decompiled and analyzed manually in detail. The 198 samples come from the malware genomic project, Drebin and Androzoo. The second dataset, which we name ALL9452, consists of 6,233 benign apps 3 and 3219 malicious apps. These apps were analyzed automatically to ensure that the benign set does not contain malware. We sent all the apps in this set of VirusTotal, a public malware scanning service. For example, if an app does not have permissions to send SMS and receive SMS, it is impossible to have the SHB delete message option. Moreover, in order to make sure that the samples are malware, we send them to VirusTotal. If an app was reported malicious by less than 2 scanners, we removed it from the malware set. And the next one is like platform. The static analyze tool ran on an 8-core Intel Xenon i7-4770 with 2 GB of RAM. The system ran Ubuntu 14.04.1, Linux kernel version, which is 3.13.0, 32 generic effectiveness. And the next one is effectiveness. The test for evaluating effectiveness consists of 2 steps, which are SHB detection validation, which is a manual process. And the next one is large scale measurement, which is an automatic process. And manual cross checking on MA198. As there is no existing oracle to determine SHB, we manually verified each static analysis report. Specifically, we reverse engineer each app, decompile the app to the source code via the JADX decompiler. Note that decompilation is not always possible due to obfuscations. So some of our manual analysis was based on source code inspection and some on Dalvik bytecode inspection. And the next one is like table, which is effective results on MA198. Our tool has reported 265 SHBs in total. Out of this, 219 were true SHBs, while 46 SHBs were over-reported false, which is like false positives, and 27 were false negatives. That is, our tool missed those SHBs due to the reason. We will be discussing that in the next section respectively. So this yields an F measure of 85.71%, indicating that our tool is quite effective. And next is like a table 4, which is effectiveness results on AA9452. We now turn to discussing the largest set results shown in table 4. Note that here the numbers in column 2 to 4 indicates apps, but not the SHBs. 311 samples from the malware set, hence the recall value is 90.62%. The tool also reported 996 benign apps as having SHBs. False positives are FPs from the benign set. Hence, the precision is 84.02%. While these 996 apps were not malicious, their use of SHP is questionable. Finally, the F measure is 87.19%. The malware set exhibited 1.5 SHP per sample on average, while the benign set exhibited only 0.2 SHP per sample. Thank you, Professor. The remaining topic is gonna explained by my teammate Sisindri.
Hello. Hi, Professor. This is Sisindri Rachakonda. I am continuing the discussion from false positives. To better understand the cause of false positives in the below, you have grouped them by self-hiding behavior. Self-hiding behavior, hide activity, hide notification, hide icon, hide app, and delete system log generated the most false positives. You investigated this and found that the false positives in the below you are grounded them. Certain apps employ a self-hiding behavior such as running in the background without the user having started the app, without the user being able to see the running app in the name of improving your user experience. I'm coming to second point, static analysis. Static analysis alias data flow and control flow analysis are over approaching which is inherent to static analysis. You have categorized a false negative source follows parameters of SHBS. Dynamically send our remote control service. Hence, your set static analysis cannot define the behavior. For example, spyware as a remote service that sends ID, time, and phone number through the network, delete certain SMS, MMS messages. SHBs are launched by GUI interaction, but the behavior missions or controls show the SHB launched by GUI interaction, but the behavior mistakes and content show the on the GUI. For example, some malware samples does not have SHBs, through they do invoke SAPI calls, tool towel root, and fake CMMC. Our tool did not identify these example as malicious. Efficiency. Running our tool in the 9,452 apps took about 10 days. The bytecode size ground columns show that the data sets had and some apps bytecode size was the large and 24 MB. Running our tool on the 9,452 apps took about that 10 days. You show the deleted efficiency results by the bytecode size ground column shown that the data sets had substance variant in terms of app size, and some apps bytecode size was large 24 MB. The time grouped column show running time statistics for the each data set. You focus on AA for 9,452. It's larger, hence your respectively. The mean analysis time was 84 seconds, while the median was 30 seconds, which showed that our analysis was practical. Finally, you behave that even maximum analysis time of 15,290 seconds. That means 4 hours, 50 minutes. Acceptable for static analysis. With a medium analysis time of 37 seconds of medium app size of 2.4 MB, you behave that our approach of efficient SHB analysis. Thank you all. My friend is continuing thread. My friend continued to share thread.
Hello, this is Charith. I would like to continue the discussion on self-hiding behaviors. A two-part focused manual analysis has been conducted for each SHB category detected in apps by our tool. First, we inspected the disassembled bytecode and then we ran the program with instrumentation. In order to validate the SHB, we concentrated our inquiry on two issues. One is the apps that are extremely popular and less popular applications that exhibited. SHB in its most severe form, we hope to provide the answers to the following questions. What causes this self-hiding behavior and what are the consequences for the end user? So the above provided is the brief summary for the above section. So regarding this hide app, after receiving the boot completed event, several popular programs such as Airbnb and BBM start themselves as an automated service. This event alerts the app that the system has restarted and requires the permission receive boot completed. There is a function that runs auto start services in the connection with this event and authorization. This is reported by our tool as hide app self-hiding behavior. This approach is used by apps to initialize app-specific information and functionalities at starting. While it may be argued that the app is not concealing maliciously, we feel that customers should be aware when this occurs. So in the hide icon, in the benign apps, the icon is added to start screen after installation. A malicious app hides from the user by removing its icon in order for the user not to notice the app's presence. While this deletion just specifies that activity should display as the first activity in a task, it is clear that a defective app may utilize hide icon to promote other activities while concealing the defective app beneath. This is exhibited by a number of popular programs including ES File Explorer, Next Launcher 3D Shell Lite, etc. But one of its distinguishing characteristics is that it renders 3D icons and widgets over their original counterparts. App ES File Explorer includes the ability to draw over programs, which is unusual and may be considered overkill for a file manager. Next comes the mute phone. The audio manager was identified to be in use by our tool. This is a camera program that edits and shoots images, and as the name implies, it has over 100 million installations and was named the best app of 2016 on Google Play in many countries. When recording the audio, camera applications employ volume controls. Our instrument self-hiding behavior was also detected in select popular places as mute phone. Because of the use of apps such as Smart Truck Route and All-in-One Toolbox. In terms of Smart Truck Route, the app checks and manipulates the data directly, audio options, including the ringer mode in all terms of All-in-One Toolbox. The software mutes the phone based on the device's SDK version, where the above statement is questionable. Next comes the hide notification. Hide notification manager is used by the number of apps, including the Waze, Truecaller, All-in-One Toolbox, Quick Heal, Mobile Security, and Minifeaton. To disable the alerts without requiring user involvement, use the cancel all command. As a result,
these apps are labeled with the hide notification self-hiding behavior. As a result, this is due to the nature of cancel and cancel call functions, which cancel all the previously shown alerts. This is due to the nature of the apps to update the user to the most current notice or combine the alerts, particularly in communication apps like Minifitter and Truecaller. For the same reasons, several cleanup and device maintenance apps have recently begun to display similar behavior. Although consolidated alerts appear to be more convenient for the user, the app does not provide a way to display high priority notifications. Next, we discuss about the block message. Given that broadcast receiver is often an inactive app component, it is not unexpected that its methods might be classified as self-hiding behaviors. Many seemingly harmless programs might reveal this type of conduct. Surprisingly, these programs are not restricted to those which significantly relies on the broadcast receiver. For instance, let us consider the well-known app for navigation, Waze, which may be interrupted as the self-hiding behavior block message. So this method is used to stop a broadcast, prevent other receivers from receiving the broadcast, resulting in blocking the intersection between the GPS and the mobile. This strategy is used to keep itself from becoming location-based signals that may be irrelevant or bother someone to the user, whereas the message blocking apps aims may disappear to the innocent, such as blocking eliminations, the user's ability to make decisions. And one more is the block call. So Truecaller, let us take the example as a Truecaller, which is a harmless program whose main goal is to identify the phone numbers and prohibits spam calls. Therefore, it was clearly noted to have this behavior, despite the fact that it specifically states that it immediately prevents the calls. An app that determines whether calls are spam for the user and can be intentionally exploited in the user's favor. So next one is about the delete call log. The app has call screening capabilities and explicit permissions to read and write call records on the user's device. Nonetheless, users may be unaware of security consequences of log deletion, and the user does not initiate call deletion. There are two elements that combine this form. This specific SHB is pretty difficult. So there is one more, that is delete call log. Minifitter, as we have taken example above, a Baidu app store app delivers free SMS to the user's contacts. Despite the app's seeming simplicity, we discovered two extremely suspicious actions. The software first deletes the system log using the logcat-c as a command. Second, the app includes the MobiClick agent activity that sends the device logs to the third-party server. As a result, the program can alter and exfiltrate the system logs without the user's knowledge. While this self-hiding behavior is not found in many other applications, users should be wary of any program that sends device logs and user information to the third-party servers. Thank you, Professor. My teammate Shiva Teja will continue the discussion.
Hi, Professor. I am Shiva Teja and I will continue the presentation on related work. So, behavior-based malware detection for Android has been long studied due to the prevalence of malware in the Android ecosystem, and a variety of methods for characterization and behavior-based detection have been proposed. Malware behavior characterization. So we have copper droid characterizations, malware behavior based on how it is initiated, either through Java, JNI, or native code execution. So it is an automatic VMI-based dynamic analysis system to reconstruct the behaviors of Android malware. And the next one, Smart Droid, uses a combination of static and dynamic analysis to detect conditions as a way to expose the behavior of Android malware in UI-based triggers, machine learning. And the next one is CrowdDroid, uses CrowdDroid sourcing to obtain traces of an app's behavior. So it is uses crowdsourcing to obtain traces of an app's behavior. It distinguishes between benign and malicious apps of the same name and version by detecting anomalous behavior using k-means
Some limitations include having to rely on the Android user community as a source for app traces, as well as having high energy consumption on devices. And the next one is Drebin. Drebin uses both static analysis and machine learning to optimize analysis and detection patterns. It is a lightweight method for detection of Android malware that enables identifying malicious applications directly on smartphone. And next one is Droid Ranger. It uses a permission-based footprinting scheme to detect malware, followed by a heuristic-based filtering scheme to identify behavior of unknown malware families. So it uses a permission-based footprinting scheme to detect malware, followed by heuristic-based filtering scheme to identify behavior of unknown malware families. Droid Detective detects malware based on permission combination by obtaining permission combinations which have been requested frequently by malware. It auto-generates sets to be used as a means of identifying malware. Next, AV class performs massive scale malware labeling through clustering antivirus labels and identifying the most likely family names for each sample. Similarly, Euphony categorizes malware samples based on clustering the antivirus labels produced by antivirus vendors. Another signature-based tool is Droid Analytics, which collects, manages, and extracts malware and analyzes mutations and repacking methods. Similarly, Droid API Miner uses classifiers based on semantic information from the bytecode of apps, namely API calls. Using data flow analysis and frequency analysis, it captures the most common and relevant API calls used by malware. Focus on a structure of information flows gathered through the sequence of API calls and the pattern of behavior present to identify malware. Similarly, we have employed such API and data flow analysis in our work to analyze SHP. Rather than focusing on general behavior-based analysis of malware, we implement a range of static analysis to detect SHP and malware. Finally, our work differs from dynamic analysis-based approaches in the standard static versus dynamic analysis way. Due to static analysis, our approach is prone to false positives, but not require running the app. And dynamic analysis is prone to false negatives and requires high quality inputs to ensure good coverage. And conclusion, motivated by the common tendency of Android malware to self-hide in order to detect, deceive users, and cover malicious traces, we define a set of self-hiding behaviors and construct a suite of static analysis to reveal such behavior. And our experiments indicate that the presence of self-hiding behavior is strongly associated with malice in a given app. Nevertheless, we also found plenty of benign, widely popular apps that employ hiding techniques, which suggests that end users and marketplaces would benefit from using an approach like ours to shed light on potential nefarious behavior in Android apps and improve user experience. For example, Dash secret folder and keeps safe calculator vault. It will take a picture when a person inputs the incorrect password. And this is the end of our presentation. Thank you, Professor, for giving us this opportunity.